So down here at the bottom of page 3 is a change of base. And so it's one of those things where sometimes we don't have the perfect number or the mental math to do it where we want to change our base. So if we wanted to find log base b of m, where b is not very common, we can just take log of m, our original, over log of b, our original base. And this log can be any base. Like if you wanted to change it to base 4 for some reason, you could, but it wouldn't help you. So most of the time this will be log base 10 that we use or the natural logarithm that we'll use. So on the top of the page 4, I had already started without recording. I rewrote our change of base formula, where again you're taking the log of a new base of the original thing you're taking the log of over log of the new base of your base. And so this one said, find log base 5 of 8 using the common logarithm, so that's just base 10. So we don't need to write it, base 10. We just write log of the original, 8, over log of the original base. And you just throw that in your calculator. The key thing when you put it in your calculator, guys, is that a lot of times, depending on what calculator you have, it'll automatically open up a parenthesis. So before you divide by that second log, close off your parentheses. So for example, I'm going to do log base 8. See how I have a parenthesis there? Make sure you close off the parenthesis, because if you don't, it's going to take a log with the inside a log, and that's not what we want. And then divide by log of 5. And remember, we kind of talked about this. What power do we need to raise 5 to get 8? Well, 5 to the first is 5, 5 to the second is 25. So we know the number is going to be somewhere between 1 and 2, probably closer to 1, because 8 is closer to 5 than it is 25. And look what we get. We get 1.29. And so that's the whole idea. If we write, watch this real quick. If I do 5 to that power, I should get 8, right? That's the whole idea. This is the exponent that I need to raise 5 to get 8. Ooh, isn't that crazy? You can go backwards. But let's write this down to 4 decimals. So this is 1.2902. Oh, yeah, I switched it. Thank you. 1.2920, not 02. I saw the 02 in the back, but that's later. So my math lab will tell you what to round to. Usually it's 3 or 4 decimals there. All right, so now what we want to do is we want to find log base 5 of 8 using natural logarithms. Should our answer be any different? No. Log base 5 of 8 is the exponent in which we need to raise 5 to get 8. So we should get the same answer, but they just want to show you. It doesn't matter what base you use, you're going to get the same thing as long as you use this formula. So natural logarithm is base e, or the natural log, right? So we'll do the natural log of the original number, 8, over the natural log of the original base 5. Okay? So when you put that in your calculator, again, just make sure you close off your parentheses there. So natural log of 8 divided by natural log of 5. When you hit enter, guess what you get? The exact same number. And that's what should happen. That was the whole idea of what a log is. Okay? So that's going to be 1.2920 again. So when you do the change of base formula, oops, I was like way up high. Whenever you do the change of base formula, you can use any base, but the only bases that are on your calculator are base 10 and base e, or natural log. So that's typically what we use when we do the change of base formula. Okay, so then we're going to get into graphing. The key thing with graphing is, I know I didn't get too in depth with graphing exponentials, but when it came to exponentials, you always had 3 points. If your x was -1, it was just whatever your base was to the -1 power. So say it was base 2, 2 to the -1 power was 1/2, so it was low. If your exponent was 0, anything to the 0 power was 1, so we always had the plot 0, 1. And then on the right-hand side of the y-axis, we always graph x equals 1, so that's 2 to the first. So again, I'm going to go back to this original, way down here. When we graph exponents, this is technically -1, 1/2, because 2 to the -1 power is 1/2. This is 0, 1, because 2 to the 0 power is 1. And then this point is 1, 2, because 2 to the first power was 2. Now we're going to have that with logarithms, but everything's flip-flopped, okay? So instead of graphing -1, 1/2, we're going to graph 1/2, -1, or whatever the base is, okay? So let's look at our function here. So this is base 5. One of the easier ways to do it, guys, is again just to think of it as the opposite, okay? So that's the inverse of y equals 5 to the x. So how would that be written? X equals 5 to the y. And we can just make a t-chart. And what's weird is instead of picking x values, we just pick our y values, okay? I know. And we cannot pick, I just pick kind of -1, 0, 1. I just think that's just the easiest. Just like I would have picked x being -1, x being 0, x being 1. So how do you figure this out? What's 5 to the -1 power?
-5.
Nope.
Wait, how's the 5?
Nope.
Oh.
1/5, right? -1 means I'm in the wrong spot. I need to go to the basement, right? I need to go downstairs. So that's just 1/5. So the first point we're going to plot is 1/5 -1. All right, what's 5 to the 0 power?
1.
1. So the next point we're going to plot is 1, 0. And then what is 5 to the first power?
5 over 1 is 5.
Just 5. You got it. So that's just going to be 5, 1. All right? So those are going to be 3 points that we're going to have enough to graph, all right? So 1/5 means we've barely moved over at all. So we're really close to the y-axis, but we're going down to -1. So he's just barely moved at all right here. And then 1, 0 is right here. And then we're going to 5, 1, so we got to go over 2, 3, 4, 5, and then up 1. Okay? So again, it's the curve, and what you're going to notice is now instead of the x-axis being our horizontal asymptote, our y-axis is going to be our vertical asymptote, right? We're not going to go past this. So he is the inverse of 5 to the x, right? Like if we graphed him, he'd be like at -1, 1/5, 0, 1, 1, 5, and he would just go right there. All right, graph it on your calculator just to double check. This is kind of a good reminder of what we just learned, change of base. Can we do log base 5 in our calculator? No. So what we're going to have to do is we're going to have to write this as log base of x over log of 5, right? This is our original function we're trying to graph. It's always log of the original over log over the base, okay? So in our calculator, what we're going to do is we're going to, again, be very careful about closing off our parentheses stuff. So you go to the y equals, clear that out, and we'll do log x, close off your parenthesis, right, over log of 5. Oopsie, log of 5, close off your parenthesis, and you hit graph, and you should see it. Mine never really shows, it depends kind of what one you have. Some of the newer ones are a little bit better. Mine never really shows the vertical part going down. Yeah, the tail end. So we know it's going to that point and just kind of riding that y-axis downward. Okay? We don't need to really plot it if you don't want. We'll just write same. We don't need to graph it, right? But I just want to make sure that you guys know how to put that in your calculator, because like, worst case scenario in a test, you're like, oh gosh, I don't remember how to graph these with points or anything. You do want to remember how we put it in our calculator, okay? Let me double check at the end to see what's going on, okay? Because it might just be you're zoomed out too much. Will you hit zoom, the middle button, after you hit graph? Hit zoom, and then, what is it, standard 6? So sometimes if you're zoomed out too much, even this little part here, this arm, kind of blends in with the x-axis if you're zoomed out too much, and so then you don't see it. Okay, is that okay? So our original, guys, we have not shifted it left, right, up, or down. Our original points were just these 3 right here. All right, so let's go ahead and flip it over to page 5. What are we going to start doing? We're going to start shifting it, okay? So it says, graph each of the following. Describe how each graph can be obtained from the graph of y equals natural log of x. Give the domain and the vertical asymptotes of each function, which are easy to do after we've graphed it, okay? So what they want us to do is plot the original on the first graph, so natural log of e, but I'm just doing exactly what we just did before, okay? So the opposite of so what's our base? This is base e, right? So the opposite is x equals e to the y, okay? So, again, I just picked -1, 0, and 1. And I'm going to do this, but you're going to kind of get in the habit. Anytime you pick -1 as an exponent, it's just the flip. So this is just 1 over e. We'll put that in our calculator, but it's going to be roughly 1/3-ish, okay? Because I know that e is roughly 3. So 1 over 3 is 1/3, right? E is 2.718, blah, blah, blah. It's like pi. It's a number that goes on forever. What's anything to the 0 power?
0, but what
One.
is?
1, right?
Oh, never mind.
And what's e to the first power? Just e, okay? And I'm writing e, but we're going to say it's roughly 2.7, so like closer to 3 than it is 2.5. All right, so when we go to graph the original, this is a fraction that's pretty small. And if you don't believe me, just put it in your calculator. 1 over e. See that guy? So he's not quite a half, okay?
How do you get that?
He's above the division symbol.
Oh.
So if you just want e, you just do the division. If you want e raised to the power, you do the second with the natural log. Okay, so we're going to barely go in 1/3, and we're going to go down to -1. Oh, what do you know? It's about the same point we just graphed with 1/5, right? 1/5, -1. And then what point did I say is always on the original graph? 1, 0. And then remember, if you're not too sure what e is, just hit second e. Just get an idea what e is. It's 2 point something, okay? So it's almost 3. So we're going to go almost 3 over, and then up 1. Okay, so he's going to kind of mimic the one we just drew. He won't be as steep because the base is just smaller. So that's our original, all right? So looking at A, what have we done to this original? What's this +3 on the inside do?
You're gonna shift it left.
Left 3, exactly. It's the same kind of idea. If I had a +3 up here, it would just take this whole graph and raise it 3. But since I have a +3 on the inside, it's a horizontal shift either left or right, and it's the opposite of what you think. So this is left 3, okay? So all we're going to do is take those 3 points we just plotted and just try to move them over 3, okay? So remember, he was just barely past the y-axis. So we're just barely past the y-axis, and then 1, 2, 3. So he's just barely before -3. He was at 1, 0. So when we move him over 3, he'll be at -2, 0. And he was at e to the first, but e was like 2.7-ish, right? So when he's at 2.7-ish, we move him over 3, 1, 2, 3. So he's at like almost just kind of past the y-axis there. All right, another thing to kind of keep in mind, which I did not graph on the original, and I feel like I should, is that vertical asymptote, right? What we were not crossing was x equals 0. So guess what? That vertical asymptote has been shifted to the left 3. So what are we not crossing? X equals -3. I think that helps you to graph that first, so then you kind of know what your curve's doing, right? Like that. It'll also help us with our domain, okay? So remember, we can't take logs of anything that's negative. So we have to take a log of something positive, not even 0. It has to be greater than 0. So the original's domain was 0 to infinity with a parenthesis at 0. But now what's our new domain?
-infinity to -3.
No, because we can only graph the right side. So what's the furthest left we can go? -3, and then to positive infinity. Yep. So remember, it's what you can graph. So we can't go to -3. We can just ride that, and then we can graph any positive x value going in this direction. Where's our vertical asymptote? It's always going to match that starting point of your domain, or that ending point of your domain, right? So x equals -3 there, we graphed it. Or remember, the original is always at 0, so wherever you shift it left or right, that's where the new one's going to go. Okay, let's look at this next guy. He's your normal natural log, so keep this in mind so we can draw him real quick again off of this. He's your natural log. But what's this negative on the outside do?
Shift it down.
Nope, because it's not a -1.
Oh, make it reflect.
It reflects about which one?
The x.
Uh-huh. And what's this +3 on the outside do?
That makes it shift up 3.
Up 3. So this first graph, guys, I'm just going to mimic the first graph that we drew right above it, right? So we already have like the points right here. Remember, 1 over e was like 0.3-ish? and he was at -1, so barely past the y-axis and down at -1. And then 1, 0 is always on our graph. And then your base up to 1 is always, so this was base E, so our base was like 2.7-ish, and then we go up to 1. So we go over to 2.7-ish and then up to 1, so it's like that. And what was our vertical asymptote to start off with? X equals 0, absolutely, okay? So go ahead and draw that curve, ride the y-axis there. Okay, so when we go to do the shifts, you shift from like the closest thing first to the furthest thing out. So the first thing we're going to do is we're going to reflect first. So let's do the reflection, and then the third thing is we're going to take this guy and raise him up 3, okay? What is a reflection? It means we just changed our y value. So here it was 0.3-ish -1, now it's going to be 0.3-ish +1. Remember, we're just going to flip our negative y's are going to become positive, and our positive y's are going to become negative. How do you change 0? 0 will just stay 0. So we'll be at 1, 0 still. And then remember, this was like 2.7-ish up a +1. So we're going to be 2.7-ish down to -1. What is still our vertical asymptote, though?
0.
0, right? We haven't moved it left or right, so we're still going to kind of ride along this x-axis or the y-axis. We're just going to be going this direction now. Whee, like that. See how he's been flipped? What's the last thing we need to do? Bump him up 3. So we're going to just physically take each point and go up 1, 2, 3. So remember, he was barely past a third and he was at 1. So he's barely at a third and he was at 1, but we got to move him up 3. 1, 2, 3. He was at 1, 0, so we'll go to 1, 0, and then we'll go up 3. 1, 2, 3. He was at 2.7, -1, so that's where I'm going to start. 2.7, -1, but then I'm going to go up 3. 1, 2, 3. So he's at 2.72 now. We have not shifted him left or right, so guess what is still our vertical asymptote? X equals 0. He's still that crazy curve. It's just now he's been shifted up. Oops, I'm kind of off the chart, sorry. All right, so domain and vertical asymptote are still the same domain and vertical asymptote as the original, right? We haven't moved it left or right any. So what's our domain going to be? Look at your original function, look at your in function, it doesn't matter. What's the furthest left we go? 0. Do we include 0?
No.
No, we write along it, so we're going to have a parenthesis there
Infinity.
to infinity, because this graph goes on forever, right? And then where's our vertical asymptote still? X equals 0. We are, aren't we? I didn't even flip it, okay?